Okay, let's do some applications now. So first thing you have here, I just copied this from the text, is just kind of a summary of some of the counting techniques that we've used so far. So from before, the fundamental counting principle says that if one event can occur in n ways and the second event can occur in n ways, then the number of ways the two events can occur in sequence is m times n. So again, in that order. So we saw that again a few videos ago. Today we also learned, or in this section of lectures, we learned about permutations, first using the idea of factorial, and then using the formulas for permutation. So there's two different formulas here for permutations we want to keep in mind. You have your standard formula, and again, this is when order matters. So something like first, second, third. So those are very distinct places. If let's say Joe gets first place or Joe gets second place, those are two very different ideas, right? So the order here is important. If you have repeat objects, though, you have a slightly different formula to use, so you just want to keep that in mind. And then we have the idea of combinations. So when order is not so much important, right? So we can use our combination calculator instead here. And then you just have some study tips here that basically says what I just said about when to use which formula. So let's do some examples. A student advisory board consists of 17 members. 3 members will be chosen to serve as the board's chair, secretary, and webmaster. Each member is equally likely to serve in any of the positions. What is the probability of randomly selecting the 3 members who will be chosen for the board? So think about what's going on here. I have a total of 17 members. They would be distinct, right? So we don't have an issue of repeated members here. You wouldn't have one person counted more than once. You have 17 different people. And 3 members are going to serve as chair, secretary, and webmaster. Now, these are 3 very different things. So the order does matter here, right? If someone gets chosen as chair or someone gets chosen as secretary or webmaster, those are very different things. So order is important here. And we're going to be looking at permutations in this case. So R equals 3 because we're choosing 3. All right, so we have 17 P3 for our formula. So we're looking at 17 factorial in the top. And then in the bottom, we're looking at that n minus r. So 17 minus 3 factorial in the bottom. Well, this is 14. Now, when you simplify, right, you have 17 times 16 times 15. And then what's going to happen is after the 14, it's going to actually just cancel with that denominator, right? Because we're going to be doing that same multiplication all the way down. So we're really just multiplying 17, 16, and 15. And what we get here is 4,080. So the number of different permutations, that we can have is 4,080. And again, if you don't want to do this by hand, you can use your calculator, but it's pretty quick. Now, you just want to be careful. The question didn't ask for how many permutations. It asked for what's the probability of randomly selecting the 3 members. So the probability of selecting a specific order, we'll say, of 3 members is 1 out of the 4,080 different possibilities, right? So for you to actually choose the 3 people, that's one specific combination out of the 4,080 possible combinations here. So just be careful. We wanted a probability, not just the number of possibilities. So our total number of options is 4,080, but we're just choosing one specific permutation of that. So you get about 0.0002. All right, let's look at a couple more examples. All right, so find the probability of being dealt 5 diamonds from a standard deck of 52 playing cards. And again, we're talking about probability here. So we need some sort of part and some sort of total to find that probability. So the first thing we need to figure out is, well, what's the chances or how many different combinations or permutations of these, combinations of these 5 different diamonds could we get, right? How many possibilities are there? So you want to be careful here. If you think about a deck of cards, there's 52, and there's 13 of each suit, meaning that there's 13 diamonds in that deck. So there's 13 possible diamonds, and we're choosing 5 of them. So your R is 5 here. Now we're going to use combinations because the order doesn't matter, right? As long as I choose any 5 diamonds, it doesn't matter the order, right? If I choose an ace first and then a 2 or a 3, it doesn't matter. Just diamond, 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 right? That's all we care about. So we're looking for combinations here. So we're looking at 13, C, 5. So that's going to be our part, right? This is what we want. This is the part that we're looking for. How do I get 5 diamonds? Well, the other thing we have to figure out is our total number of possibilities for getting 5 cards. So think about a deck of cards, right? There are 52 possibilities there, and you're getting 5 of them. So how many different combinations can we make there? And again, the order doesn't really matter here. It doesn't matter if we get a king first and then a queen second or something like that. It's just altogether 5 cards we're looking at as a group. So we're going to use combinations again. So your N is 52 here because it's 52 options. And again, your R is going to be 5 because we're pulling 5 cards. So we're looking at 52, C, 5. So if I figure these values out first, now you could definitely use your calculator here. I'd probably go ahead and suggest that just to save a little bit of time since we're doing a couple different combinations. So if I go back to my math feature and I plug this in, I'm going to use 13 and then 5, and I see that I get 1,287 possible ways to get 5 diamonds. And then over here, I have 52 again with 5. I have, let's see, 2, 5, 9, 8, 9, 6, 0. So I have 2,598,960 ways that I could get any 5 cards in a deck of 52, right? And again, the order doesn't matter here. So we're not saying it has to be in a certain order or you're being dealt, one first and then one second. It's just you're getting 5 cards. What combinations could you get? So our probability then is going to be this 1,287 divided by this 2,598,960. And what you get here is about 0.0005. So the chance of getting 5 diamonds is very small, right? It's only 0.0005 for a probability. Okay, let's look at one last example here. And again, we're going to just be a little bit careful, read through. These can get really complicated. It says a food manufacturer is analyzing a sample of 400 corn kernels for the presence of a toxin. In this sample, 3 kernels have dangerously high levels of the toxin. 4 kernels are randomly selected from the sample. What is the probability that exactly 1 kernel contains a dangerously high level of the toxins? Again, we're looking for a probability here, not just a count. So this is what's going on. We have 400 corn kernels, and in this batch, there are 3 that are toxic out of the 400. And you are going to randomly select 4 of them. So we want to know what's the chance that you will get 1 kernel in those 4 that is toxic, right? So there's a chance of 3 out of 400 that are toxic altogether, and you're going to just choose 4. So what's your chance that you're going to get 1 of those bad kernels in your sample of 4 that you're choosing here? Okay, so let's think about a few different things here. So again, if we're looking for a probability, you need some sort of part and you need some sort of total. So you gotta think that way. So I need some count for my part and I need some count for my total. And I'm looking here for the probability that exactly 1 kernel is toxic, right? So I want the probability that exactly 1 kernel is toxic. Now we're choosing 4 kernels here. So we want to know if exactly 1 of them is toxic, then 3 of them are not toxic. So in the part here that we're looking at, right? Because we're looking to choose 1 toxic kernel. What's going to happen is we get 1 that's toxic and 3 that are non-toxic. right? Because again, it's not more than one, it's exactly one. So you get one that's toxic, three that are not. Now, it doesn't really matter the order in which you do it in, right? It doesn't specify you have to choose it first or second or third or fourth. So as long as any one of those four are toxic, then you have a problem, right? So what we're looking for here is how many ways can we choose one toxic kernel and how many ways can we choose three non-toxic kernels? So the number of ways that we can choose one toxic kernel, well, there are three kernels altogether that are toxic, and we're choosing one. So our calculation here is 3, choose 1. Now for non-toxic, let's think about it. There's 400 altogether, and there's 3 that are toxic. So 400 minus 3 is going to give us 397 kernels that are not toxic, right? And we're choosing 3 of those. So our formula here is 397, choose 3. Now we can use the fundamental counting principle here to finish this idea. So we're going to choose 1 toxic and 3 non-toxic. So we're going to multiply these 2 counts together to get our total. So for the first group here, again, you can use your calculator. What you get here is just 3. And then for this group here, you're going to get 10,349,790. And again, you can use the calculator the same way I did in the last problem to make this a little bit easier, because now our numbers, again, super large. And we have 31,049,370. So there are 31,049,370 different ways that we could choose 1 toxic kernel and 3 non-toxic kernels. So that's the part that we're looking for. That's what we're trying to do. Now, what is our total? Well, our total is just however many combinations of 4 in general, right? So we actually have 400 total kernels, and we're choosing 4 out of the group. So we're looking at 400, choose 4. And again, really large numbers here. You get 1, 0, 5, 0, 7, 3, 9, 900. So you're up at 1 billion different ways to choose 4 kernels from 400. And again, the order doesn't matter here, so we're just choosing 4. So finally, our probability then is going to be that 31 million over that 1 billion. And we get about 0.030 using 3 decimal places. So looking at this as a percent, if we multiply this by 100, it's about a 3% chance actually that you would get 1 toxic kernel out of 4 to choose. So I know 3% is low, but that's pretty high, right? If someone made a bet with me, say, hey, do you want to do this? I'd be like, no, a 3% chance is too high. That's a pretty high chance to actually get a toxic corn kernel out of 400. So when you're doing these questions, they can get quite tricky. They really can. So you want to think about, first of all, does order matter or not, right? If order matters and the distinct ordering makes a difference, then you're looking at some sort of permutation. And there's 2 formulas there that you would choose from. If order does not matter, then you're looking at some sort of combination. So at least you can kind of start in the right direction. Your N is always your total, and the R always represents how many you're choosing out of that total. And then from there, again, if you're doing probabilities, you're not just finding the counts, but you want to think back that a probability is always this idea of part over total. No matter really what kind of probability you're doing, it's still that same concept of part to total. So you want to find out the part that you're looking for and then your total count in each of those cases.